Well, good afternoon, everyone. I hope you can hear us pretty well. So thank you for joining us for this edition of the CATS Clinic again. So Dr. Anikazi will be taking us with the next lecture in this series, which is going to be comparing means. So Dr. Anikazi, please go ahead.
Hello, everyone. Yeah, good day to you all wherever you are. I'll be leading today's session, which has been titled Comparing Means. And we'll just dive in. Dr. Matai will be supporting me. So if you have any questions, please feel free to put that in the chat and he will help out with that. So I don't know how many of you here were here in week 1. And for those of you who were here, I'm wondering if you remember this slide from week 1, where we were talking about measures of central tendency and we dealt with mean, median, and mode at the time. If you recall from the week 1 lecture, that the mean is heavily dependent on the distribution being described as normal, and that in those normal distributions, you have the mean, the median, and the mode being equal to one another. And for the mean being the preferred measure when there's a normal distribution. However, when that distribution is not normal, the median becomes the preferred measure. I don't know if we all remember that from week 1. If we do, I would ask who can tell us one of the things we talked about that defines normal distribution. You can type in the chat. Just one volunteer to tell us what the things that define normal distribution. Okay, I'm not seeing any chat coming in, so let's move on. For us to define something as normal, if you still on your screen, if you're looking at it, you will see the image at the top right-hand corner. You will see that, okay, thank you. I see one coming. The mean, the mode, and the median being equal, that's 1. 2 is that it's symmetrical, right? If you look at it, if you draw a line down from where you have 100 and the X to the top, you will see that it looks like mirror image of one another. If you do that, that's another, okay, the tails are the same. Good, thank you for that. And you could say it's unimodal, meaning it has just one single peak. You see that's the peak where it aligns with 100. There's no other peak here. And one other thing you could use to define normal distribution is the standard deviation. Okay, where, yes, thank you for that. If somebody just volunteered the z-score there, but let's use the percentages. You would say that about 68% is approximately within one standard deviation. And about when you move to 2 standard deviation, that moves to about 95%, which equals this score that was put in the chart, this score of 1.96. And when you move out to 99 percentile, you have that's about 3 standard deviations. So bearing this in mind, we're moving from talking about just a single set of data to comparing groups of data here. So even though we call this comparing means, it's actually comparing groups of data. That's what we're going to be looking at this week, really. And we're going to be focusing on those data sets that fit the characteristics or the parameters of a normal distribution. So those are called, the tests that we use in these scenarios are called a parametric test versus scenarios where we have data sets that do not meet the parameters of a normal distribution. So the outline for today's lecture, for today's session, we'll be going through the one sample t-test, just as a reminder of what we have done in the past, and then we'll move on to the comparisons, where we have the paired t-test, the independent t-test, and then we round it off with the ANOVA. So going into the one sample t-test, this is usually used in scenarios where we want to test if the sample mean differs significantly from that of a given population from which the sample is drawn. So you all remember, referring again to the first lecture in the series, where we talked about the central limits theorem, that when a data is repeatedly sampled from a given population, and we calculate the means, that we tend to get a distribution that we call the sampling distribution, where you have a set of means from each of the samples that you've drawn, right? So if we want to guess or estimate the population mean, the estimate here is that if we look at the range of the means and we take the means of these means, that it should be a proper estimate of the mean of the population from which it is done. And if we look at the standard deviation of that is what we call the standard error for the population. So for instance, when we're trying to figure out if the mean of one of those samples is representative of the sample mean, and we're looking at different confidence intervals to look at it, going back to that normal distribution frame. Say we're taking at the 95% interval, we're looking at that to be plus or minus 1.96 times the standard error. Or if we're looking at the 99th percentile, we were saying plus or minus 2.58 of the standard error. So we assume that the mean of the sample we draw should fall within that range. And if it doesn't fall within that range, we end up with the assumption that it is not representative of the population from which it is drawn from. Please, as we go through this, if you have any questions or if you have any comments, like I mentioned at the beginning, please feel free to put this into the chat. So we'll take an example. We'll take an example now. So, and say for instance that a certain Dr. Samuel believes that the citizens of his town are consuming calories differently on a particular day, in this case Eid, that they do on any regular day. How do we test this assumption? We can start by getting an estimate of what the citizens consume on a regular day. We have that, and then we can go on to recruit people to test what they consume on Eid day. That's the example of us taking a sample from the population. And then we go on to calculate the mean of our sample, and then the standard error of this sampling distribution. Then we calculate the upper and lower confidence intervals. Say in this case, we're using the 95 percentile as opposed to using the 99th or 90th percentile interval. So how do we do this calculation? I will allow about 3 minutes to see if any of you will come up with answers in the chat. 3 minutes, then we'll go on to the next slide. So what will be the null hypothesis here? Remember, the null is always that there's no difference. So that will be saying that the mean you got in your step one and the mean you get when you measure the 100 folks in step two, that there will be no difference in them, right? Whereas the alternative hypothesis is that there's a difference. Now, this is, we're not trying to make this difference directional. So it could be positive, it could be negative difference, meaning it could be higher, it could be lower. I'll allow a few more seconds. We'll move into the next slide and we'll go through it together. Okay, so like I said, the null hypothesis here is saying that the means of calories consumed during the Eid is the same as the mean of the calories on these regular days. Whereas our alternative hypothesis is saying they are not the same. If we recall from the previous slide, that the mean calorie consumption on the regular days is 2001. And our nutritionist has gone ahead and measured and come back to tell us that the mean from the sample of 100 people on the Eid day is 1850. Whereas the standard deviation here is 300 calories. So calculating the standard error of the sample, where we say the standard error is equal to the standard deviation divided by the square root of the sample size. So the standard deviation is 300 and the sample size is 100. The square root of that is 10. So 300 divided by 10, giving us 30. So our going into calculation of our 95% confidence interval will be the mean plus or minus our z-score for 95 percentile, which is where we're trying to place this significance level, multiplied by our standard error. So if you do that calculation, you should get the upper boundaries and lower boundaries that are on your screen. So, and if we recall, I believe from one of our earlier series when we talk about confidence intervals, when we go to say a confidence interval of 90%, 95%, or 99%, we're simply saying that we have that confidence level that our observed value will be within that specified range of the upper and lower range. So if it falls in within that range, we can go ahead and say and conclude that there's no difference. But if it falls outside of that range, we cannot make that conclusion. So in this particular case, our observation is 2100 calories. And the 95% confidence interval for those on Eid days is 1791 to 1908. If you see, it's outside of that range. So here, we cannot make the conclusion that they are the same. Does that make sense? So we could also do this in a different way using the Z statistics, where we go on similar parameters as we had before, but instead here we're picking we're using a different formula. You see the formula displayed on the right-hand side of the screen, where we say we take the observed value, which is 2100, and the sample mean, and then the standard deviation of the sample. This is assuming that all these values are known. So we'll just simply go ahead and say, okay, the observed value minus the sample mean minus the sample mean divided by the standard deviation of the sample. So if you do that calculation, you end up with a z-score of 0.8333 to whatever decimal places you want to put that. Now we need to convert this into a p-value to know if this is acceptable at a 95% confidence interval. And I put a link on that screen for a z-table. If you have a z-table in front of you, you just have to go through it to see to get the p-value. And if you do that, you arrive at a p-value of 0.2033, which at that level, we're not able to, to accept the mean, to accept the null hypothesis. I see comments in here asking for us to go over this example again. Okay, so let's start from the beginning. Here we have let's assume this is a physician, or let's assume this is an administrator, but we just have somebody who is trying to figure out if the amount people eat on a certain day of celebration, which is the Eid day in this particular case, is different from how they eat on other regular days. And we're measuring this by calories consumed. Okay. And so in order to do this, we outline the steps that are needed. That the first step is for us to find out how many calories are consumed on a regular day by citizens of this town. So, and remember, this is the mean of the calories consumed, the average across the population in this town. Then we proceed to look at the day in question. I see people commenting that the slide is different from what they get. Yes, there are slight differences. You will receive the updated slide at the end of this. So let's just focus on going through today and not so much on the slide you received before this session, okay? So step 2, you pull your sample out of your population. In this case, we decide to pull out a sample of 100. Step 3, we calculate the mean from our sample and the standard error of the sampling distribution. Then we decide at what confidence level we're looking at this. In this case, we're picking the 95th percentile here. So we come in here to state that what's our null hypothesis. Our null hypothesis is there is no difference in the consumption on a regular day and on this day of celebration. Our alternative hypothesis is there's a difference. We're going to pick the relevant details out. And the relevant details here is what is the mean calorie consumption on regular days? That's 2,100 calories. Okay, from the sample of 100 people we pulled, what is the mean? We've been told here it's 1850, 1,850. And the standard deviation being 300 calories. Now we go ahead to calculate the standard error of this particular sample using the formula where the standard error is the standard deviation divided by the square root of the sample size. And if we plug in those numbers, we arrive at 30. Remember in the previous slide, we had said we're making the assumption that we're looking at this at the 95% confidence interval or the 5% significant level, whichever way you want to look at it. We've made that assumption if you go to the previous slide. If you look at step 5 here and step 4, that's what we talked about. So coming back in here, we make that calculation that in order to be able to get the boundaries of a 95% confidence interval, we take the mean plus or minus the z statistics that corresponds to the 95% confidence interval multiplied by the standard error. And if we do that, we'll end up with an upper boundary of 1,900 and a lower boundary of 1,792. So I did explain that when we talk about confidence interval, when we say that this is the mean within this certain confidence interval, we're saying that at that specified confidence interval, that we are confident that that particular value will fall within the range. So in this scenario where we're using the 95% confidence interval here, we're saying that we're confident that 95% of the times that the mean will fall, the mean from the sample is going to fall within 1,792 and 1,908. So if the mean we were given on a regular day falls in within this range, we would make that conclusion and go with the null hypothesis that there's really no difference. But as we can see, 2,100 calories is outside of the given range. So we cannot go with the null hypothesis. Instead, here we go with the alternative hypothesis that says that the calories consumed on Eid is different from that consumed on regular day. So now we go into the alternative method that we were discussing earlier on. Remember again, we're still holding this at the 95% confidence interval of the 5% significance level. So the null hypothesis is still the same, saying no difference, right? While the alternative hypothesis is saying there's difference. Our mean on regular days is still the same, 2100. Our mean from the sample, 1850. So, but in this particular case, we are calculating the z-score here, right? And using the formula as shown on the right side of the screen, where you have the observed value minus the mean of the sample, and then you divide that difference by the standard deviation of the sample. So good enough in this particular scenario, we have all those values in there. So that's 2100 minus 1850 divided by 300. If you plug those in your calculation, you end up with the z-score you see on your screen, which is 0.8333 onwards. Now I did put in a link in there for a z-table. You go to a z-table to look at this, to try to find the p-value. You end up with a p-value of 0.2033. So are we clear on that now? So with this, once again, we go with the alternative hypothesis. We arrive at the same conclusion that citizens of coastal town consume calories differently on Eid than on regular days. We'll have to move on at this point, so I'll just implore those that are still requesting for us to go back to view the video when it is sent out. And if you have additional questions, to please send it. So next we're moving to the paired sample t-test. Here we're talking about scenarios where the data sets, the two samples that the two data sets you're trying to compare are related, or what we call dependent samples. And we use it to test if they differ significantly. So for example, testing whether there are significant differences between two measurements from the same group of people, e.g., systolic pressure taken while sitting down versus standing, body weight at the beginning of an exercise program versus at the end of the program, an infant's weight at admission versus that at discharge. So if you say there's something, there's a relationship between these measurements, which makes us to describe them as being dependent upon one another or being paired. Now, if you're not able to get that relationship between the two of them, you cannot arrive at the conclusion of saying that they are dependent. There must be something that is tying those two data sets, that is common between those two data sets, before you can make that assumption of a paired or dependent sample. So, say for example, we conduct measurements in many participants, and say n number of participants in the study, and we have observations for each person at different time points. We can calculate the difference for each person at those time points I, which is and then go ahead to calculate the mean of the differences, which will be a summation of the differences versus the sample size. Now we can test whether this is different from the specified value using the paired t-test, where the t-statistics in this case is the mean of the differences versus what say our population mean, if we know it, which in some cases, in most cases, we really don't know what that population mean is. And then we go ahead to divide it by the standard error multiplied by the mean of the differences. So most of the times, like I mentioned earlier on, the population mean is unknown, or we set it at 0. So, and we go, and if we do that, the formula becomes modified to just be t-statistics, simply being the mean of the differences divided by the standard deviation multiplied by the mean of those differences. So our first example here would assume that you are the CMD at a hospital, and you're trying to take a survey of how many hours your residents work, and and you go ahead to calculate the mean. When you do that, say hypothetically you take your sample, and then you calculate the mean, and you end up with the output on your screen, where you have a sample size of 187 with a mean of approximately 72 hours. And you decide you want to do something about this. You decide to make some changes. In this particular example, where hypothetically saying you hire additional staff and shift some of the work that the doctors are doing, but it could be any sort of intervention. You make some intervention and time that intervention over a period of time. At the end of that period of time, you take another survey to find out how your intervention has worked, to see what the mean is at the end of it. And for you to find out if your intervention worked, if it reduced the number of hours being worked, or if it increased it, you do the paired sample t-test here. So say the time interval we chose here, which is the time I, is 12 weeks. And in that time, you've taken the measures again, and then you go ahead to find out what the differences is between week 0 and week 12. And that's the end of your intervention, at which point in your intervention you took the second measurement, and then you proceed to calculate the difference in that mean. So we go ahead in similar fashion. We're going ahead to say our null hypothesis is there's no difference, or that the difference in mean will be 0, right? And the alternative being that the difference in mean there will be no difference in mean between that. The alternative being that the difference in mean is anything but 0. That's what our hypothesis is in here, right? So we go ahead to run that, and we end up with the outputs you have on your screen, where we find out our mean in week 0 is still at approximately 72, like we said earlier on. At week 12, this is at 64. Now, how do we test if this mean of 64 is significantly different from the mean of 72? That takes us to the paired sample t-test, right? And if we run that, it gives us the output that is below, telling us that the mean difference in that time, is 7.86. Larry, please, can you take the questions that are coming through the chat, please? Okay, so we can go ahead, yeah. So focusing on the paired sample t-test, right? We see that the mean difference in hours worked is 7.86. Now, remember our null hypothesis is that there will be no difference in the mean. That's 0. But here we see that there's a difference, and that difference is different from 0, right? So, and then our output went ahead to give us the one-sided p-value, the two-sided p-value, and all that, and give us the 95% confidence interval, and so we have a lot of test statistics here to play around with. And going ahead to play with it, we see that the 95% confidence interval did not cross our null value, which is 0. If it crossed our null value, which is 0, at that point we'll be we'll be saying we'll be going with the null hypothesis, but it did not. So we could use that to make the conclusion that there's a significant difference between the mean at week 0 and mean at week 12. If we choose not to go with that and we want to look at our p-value, we'll see our p-value, both the one-sided and the two-sided p-value are quite significant also. So whether we're using the confidence interval or the p-value here, we end up at the same conclusion that we reject the null hypothesis, that there's no difference in our measurement after our intervention has happened, and make the conclusion that's of going with the alternative. Now we're going to another example where this time around where we're looking at a clinical trial to look at the effects of a new drug on systolic blood pressure of adults in Freetown, and compare the systolic blood pressure blood pressure at the beginning of the trial versus the blood pressure at 4 weeks of using the drug. Now we're giving certain values in there, and we also have the test statistics here, where the value at the mean value at the beginning of the trial is approximately 119.6 millimeter per mercury, whereas at 4 weeks is 111.7. So we have that, and then we have the PET-T test here. So who can remind me what our null hypothesis would be in this case? Remember, this is a PET-T test we're doing. Can someone volunteer to remind us what our null hypothesis should be? Okay, so moving forward, once again, our null hypothesis will be there will be no difference in the mean. Thank you for that. While the alternative will be there will be a difference in the mean. Now we're going to look at the output we receive, and the output we receive showed a difference in the mean, and that difference being 7.89 approximately, with the ranges for the 95% confidence interval being 7.44 to 8.34. And also looking at the p-values to see that the p-values are also significant. So what conclusions would we arrive given the test statistics that is in front of us? Any volunteers, given the paired sample t-test outputs that you have on the screen? Thank you very much. We reject the null hypothesis, and thank you. So, and that essentially is what we explain on this particular screen, that our null says it is 0. We look at our confidence interval, it doesn't include 0. So we reject the null. And if we decide to use the p-value rather than the confidence interval at 95% confidence interval, our p-values are also very significant, both for the one-sided and the two-sided.